What about VASP?
Yeah, VASP is running.
Now everything is running.
Yeah,
Did you check your step 2?
I submitted, but I'm not able to run this. I mean, I submitted just one is run.
Oh, okay. Like short one.
Yeah, short one, but I'm running the full one. That's it.
But at least we don't need to complain about VASP problems right now. Not now.
Not now, I'm just using that. And for login one, it didn't help when we discussed last day, and that day is crashing the whole job. So I was okay, don't bother about this one because we are going to shut down.
So who is the first?
Daniel.
So Daniel is invited to present his Literature Club contribution.
Daniel is presenting his presentation as a first presenter.
Unambiguous declaration.
So
Don't worry, it will be normal version in a second.
second.
Yes.
Oh, 1, 2, 3, 4, 5.
So this is the paper that I'll be presenting literature review on. It was long carrier lifetimes in a lead iodide rich perovskite that were then finalized with molecular dynamics. So I guess
Which journal is it?
Hmm?
In which journal was it published, this paper?
Journal of Physical Chemistry Letters.
And who's the authors? Okay.
Olaf and his group.
Ah, okay.
Is it published or under review?
I think it's under review at the moment.
Let's not disclose it.
Oh, so it's not published?
Let's not disclose it.
So I guess background to this would be a couple terms of non-adiabatic coupling, and correct me if I'm wrong, but believe that this is the equation to non-adiabatic coupling, which with the Born-Oppenheimer approximation. So it takes basically the wave function and the orbitals of the ground state with the summation of I think from what Landon was trying to explain to me, this is just a vector equation with just the wave function of the energy level that was calculated with the Born-Oppenheimer. And with this term right there being called the I think is the nuclear kinetic energy perturbation operator, along with just the wave functions of the ground state as well over the energies. Then finally multiplied by that. So from
Hey,
this-
Daniel,
Yeah.
what are the subscripts on phi? What do they mean?
On five, on this one, or
On
yes,
both of them.
on both of them.
So it looks like epsilon and epsilon I. It's kind of hard to tell.
With phi, it's I guess the first one by the equal sign is just GI, or then the one by the vectors is EV, which or yeah EU.
And what does it stand for? What is the difference between these indexes?
Well,
Or what this indexes actually corresponds to?
okay, well from the EV, it's from the it's the phi from the energy of the vibrational of the Oppenheimer approximation, which is from this one, and the GI is just the ground state.
So new states for the index of vibrational mode, or what?
So you are showing, can you please look for the first term before summation and explain what is psi and what is phi lowercase? Which of them is electronic, which of them is vibrational, and why the second factor has two indices?
But the second factor has two indices.
See, this psi has psi sub g
Yeah.
and phi sub gi.
So
G stays for the ground state, right?
the GI stood for the ground state. I think is what the paper said.
Then what is G? If GI stays for the, like, there are two indexes.
Yes, I see
GI
what you mean,
and
yeah.
G, then, well, at least some of them should be different.
Yeah. So
G and E, I guess E is excited and G is ground.
But I have a question. Did you take this equation from the paper, which you announced in the very beginning? Or you took it from somewhere else?
they didn't really they didn't show an equation to how they figured out non-adiabatic coupling in the paper. So I guess I
But
just
maybe they cite some other papers where they showing these calculations.
yeah, I see what you mean. I probably should
But
have
did
looked
you
into
take
that.
them like from their references? Where did you get this?
Where did I get this? I found it from another paper that I cited down there.
But this is where they cite to or not?
No.
Okay.
So I guess I should have probably used the one they cited to then.
Well, because again, even when we call non-adiabatic couplings, right? So it can
Yeah.
be taken with different approximations. And they might apply some approximations which might be not really applicable in some other cases. So you need to be kind of careful and probably go through the sites, through the references which they cite rather than just Google something.
Yeah. Absolutely.
Or you can Google something, but then look on their equation, right, and figure out how this formula, which you found somewhere, different from what they are using. And again, so you're saying that I'm completely lost. You said that this is taken in the Born-Oppenheimer approximation, right?
Yeah.
But Born-Oppenheimer approximation doesn't include any non-adiabatic couplings because it's completely decoupled electronic from vibrational degrees of freedom. Born-Oppenheimer approximation says that you can neglect this interaction.
Mm-hmm.
So that's why it's really strange that you're saying that you find the non-adiabatic coupling in a Born-Oppenheimer approximation because it means your couplings have to be zero.
Yeah.
So
What do you mean, yeah?
he agrees.
Do you agree with what?
With basically what she said about Born-Oppenheimer approximation does basically sum it up to equal to zero.
But you're telling that you are expressing non-adiabatic coupling in basis of.
Well, it's a different thing.
Did you miss the word basis?
Basis.
Well, he said in approximation of Born-Oppenheimer, right?
Yeah.
And saying using the Born-Oppenheimer approximation for the basis is two different things, right?
Yeah. Well, I guess as
It means you're taking your wave function, which really has couplings, and put it in a basis of those guys which don't have couplings, but with a different weights, right? It's
Yes.
not just a single orbital, but many of them. And so pretty much the same approach as we apply in, let's say, in the Hartree fork. We take in non-interacting electronic states, right? From hydrogen atom, and kind of put it in a like this is our basis, and then construct the many electron wave function.
See,
So what is your Born-Oppenheimer approximation?
well, these values of E, from I guess whatever this little paper told me, these are actually taken from the Born-Oppenheimer approximation values.
But you have two indexes. You have two letters. One is psi, another is phi or phi. How you call it?
Yeah.
How do you call it actually? Psi and phi.
I don't know how to pronounce
How
it.
you pronounce it in Greek?
That's how I pronounce them.
It's up to debate.
I don't know how to.
We do not have Greeks among
He knows
among
Greek,
us.
But you
he learned Greek.
Oh, yeah.
Oh, psi.
Phi, psi, phi, psi, whatever.
Whatever. But there are two of them, right? So
Yeah.
again, distinct between these two notations. What is one? What is the second?
Well, with the V and the E,
Well, with these two different letters. Why are you having these two different letters? The psi and phi or phi.
psi and phi.
Mm-hmm.
Well, psi wouldn't it just be the wave function, while phi would just be the orbitals? Correct?
Let's go step by step. You may stay on
When
this
you
equation
say-
for
When you
hours.
say wave function, it sounds like you're talking about many electron wave function, right?
Yeah.
But we usually don't know it. Where do you get it?
Yeah. And that's
Wait a minute,
pretty much
add a
what,
comment. This
indication
equation is
telling
not wrong. We just need to interpret it.
And I guess we need your help.
So, question to everyone: what should we cross out or just cover to return back to Born-Oppenheimer approximation?
The sun.
Yes, London won this.
What was the price? What was it?
So, if you remove sum and everything after the sum, you get the overall wave function as a product of electronic and nuclear wave functions.
Stop. He already give you the hint right away. So now you need to figure out what one is electronic and what one is nuclear. So which one?
Which was electronic.
Again,
which was nuclear.
if we say that now in Born-Oppenheimer approximation, your electronic degrees of freedom is independent from the vibrational, from the nuclear degrees of freedom, right?
Mhm.
So then you can represent the overall wave function as a product. One function stays for the, or one orbital stays for the electronic orbital, and other stays for the just nuclear. Right? If
Yeah.
the product, then they don't interact, and this is your first term. So now you just need to figure out which one is electronic and which one is vibrational, or stays for the nuclear motion, for the nuclear wave function. Well, and this should give you some ideas about these indexes probably, right?
So I believe the nuclear terms would be these terms right here, the ones with the, I guess, the subscript with the epsilon.
With one index or with two indices?
Nuclear would be with I believe with just one index.
And if you think longer?
Think longer with two indexes.
Okay.
Why they should have two indexes? Well, let's start with electronic. If electronic has just single index, right?
Yeah.
It tells you just the state, right?
Yeah.
In a quantized system. Then why the nuclear should have two indexes? Or what kind of meaning of these two?
Because the nuclear would just, I guess, depend on two different.
Well, one index probably should correspond to the index related to the motion of your nuclear, right? Which would
Yeah.
be dependent on a coordinate of nuclear motion, right? And then the other one,
just depend, I guess, on this. On the. Well,
and it
you-
looks like they have pretty much the same index.
Yeah, I guess they do. Cool.
So it means they should connect it to the electronic state, right?
Yeah.
So kind of it's a nuclear wave function which depends on a coordinate of the electron and kind of as independent variable, and the coordinate of nuclear, right? Also as an independent variable, but it still depends on both. Just these variables are independent. Means you can fix one and get the other, or backward. You can fix the first and get the other. And those which corresponds to the electron degrees of freedom, right? So they, of course, kind of should be connected to the solution of the wave function for the electrons, right? So that's why this index will be kind of connecting everything to the electronic degrees of freedom, right? And the second index will be really related to the nuclear motion. Am I right?
So why there are two indices for nuclear wave function? And generally, keep answering. Generally, if you present, you may give definition for audience.
Nice.
Oh, that's how that works.
Oh.
So why is there both the electronic and the nuclear?
Yeah, why the nuclear wave function has two indices? Why why cannot we use only the index that is different from electronic? keep only I and skip G.
Well, I guess the energies, the energies of the wave functions are just dependent on both the electronic and the nuclear.
Well, potential energy surface, which determines shape of nuclear wave function, is different for each electronic state. Therefore, one needs to have index corresponding to electrons.
And this is your connection with electron degrees of freedom, right?
Yeah.
So like if you go to very high electronic degrees of freedom, you expect that your nuclear, potential surface should be kind of related or different from those which are going to the ground state of electronic functions.
Okay. It's good to know now.
Very nice definition. If someone would ask me to introduce non-adiabatic coupling, I would never show this equation.
But we don't know what's the form of this T. You probably need to really kind of represent T with this definition. So what exactly your operator T, how does it look like?
Legitimate question.
Well, I guess.
Can you write T equals and give, or at least verbally tell?
Well, he told already what is it, but we need a formula, right?
Yeah, I guess I don't think in that paper too, our guidance form, they didn't explain what T was. They just verbally,
But you can tell.
really said it.
But repeat again, what is it, the definition?
It's basically two nuclear kinetic energies.
Can you write the operator for kinetic energy?
The operator
From
kinetic
quantum mechanics?
Top of my head,
Oh, for classical mechanics, I don't know. Start with something at least.
yeah, I guess.
Just some formula for kinetic energy.
Kinetic energy. Guess what? Formula for kinetic energy would probably just be what?
EK equals.
Oh, yeah.
This is for classical at least.
Is it on there?
That'd just be the mass times the acceleration. Well, that would be just force.
Mass times acceleration. Okay, it's a Newton. Well, I mean, overall it would be a force, not really energy, but you can get energy from it.
So then,
What's the connection between force and energy?
Kinetic.
then I guess
No. What you wrote on the top is not K, it's F. Force equal ma, based on the first Newton's law.
yeah.
But usually if you have a force acting on something, it means you're characterizing potential energy.
Yeah.
But we're interested in kinetic energy. Should it depend on velocity
Uh,
or momentum?
No, would it just depend on the potential?
Kinetic energy depends on potential,
Yeah.
and potential energy depends on kinetic. Great.
It's a trap. It's a trap. You shouldn't agree.
Oh, maybe anyone can be more successful than we are. Can you hint something? Maybe give him a hint so he can immediately, because I'm sure you have seen this formula many times.
1/2.
Oh, okay. Potential energy. But okay, let's see what it comes. 1/2. At least you should have 1/2 in your formula.
You can write T prime sub n equals 1/2.
And this would be absolutely right,
Good start.
but you need as a coefficient, right? But you need to finish with something more, with some physical variables. Does your kinetic energy depend on mass?
I believe so.
Proportional or reverse proportional, square, cubed, linearly,
Logarithm.
logarithmic, exponential,
Wouldn't it be squared? Or-
mass square. There is a square in this formula.
It's like an Einstein's formula. Energy equal mc square.
I believe the squares of the.
Oh, okay, good. Okay, yeah. So this is kind of classical form. If you write this, can you now write it through the momentum? Do you
No.
remember what is momentum?
So,
Moment of inertia, how it goes? No.
Measure of inertia.
Moment.
Measure.
Momentum is a measure of inertia, right?
No. Measure of motion. Mass is measure of inertia.
momentum.
So in other words, you have the same velocity and you have one small mass and one big mass, which will be having a larger momentum.
Which one have the larger momentum? The one that weighs more?
Okay, and now you assume that their mass is the same. You have two identical masses, but one moves twice faster than the other. Which momentum would be faster? It would be
Moves
larger.
faster.
Okay, so then actually, in this case, they are linear proportional. So your momentum equals just m times v, right? And now if you play with this formula, you already have m times v squared. Can you write it through the momentum? If momentum equals m times v, then t would be would
T.
equal to,
Oh, I guess what? Just combine those terms together, so it'd just be what? Be what? Be that? Or
what? M
no, I
squared
just
v
combined
cubed?
both the terms together.
Well, if you want, like, if we will have v square m square, then it would be momentum square, right?
Yeah.
But you have v square, but you don't have m square. What to do? In math, it's really nice. You can multiply by m and divide. Nothing is changed, right?
Mm-hmm.
But then on the top, you will have your m square. So do it and see what happens. Like multiply by m and divide by m.
You keep doing it, I just detain audience with a comment. In physics, there is a method of dimensionality. If you need to get an answer for some variable, you just write down all variables.
You just said multiply by m and divide by the momentum?
Powers until you get
Well,
the right answer.
take your 1 over 2 v square m
Yeah.
times m divided by m.
M divided by
If you multiply m divided by m, nothing is changed, right?
Yeah, it's just one. Yeah.
But multiply and see what happens. Like really write it and see how you can play with it.
Multiply by m.
And divide by m.
So I guess if I multiply by m, it's gonna be m squares.
Okay?
2.
And divided, you still have m at the bottom, right?
I have the m in the bottom in this equation. I guess the last one that I wrote.
Because you multiply by m and divided by m. You still need to divide by m, otherwise you change
Yeah.
your equation.
So what doesn't that just cancel out the square? and
But
just
you
go
don't
back
want to
the
cancel it because you want to have m square v square because it gives you p square. Now your formula will end up with what? 1/2. On the top you have p square, right? On the bottom you will have m.
P square, P, not V.
M
right.
times v is p. M square v square is the same as p square. Great.
And now by next very natural step, you convert it in a quantum form.
Now you need to remember what is your operator of momentum in quantum mechanics, right? And just substitute your p as an operator of momentum. Do you remember what is operator of momentum in quantum mechanics?
Operator of momentum.
Uh-huh. Starts with
What is
minus ih, right?
What is EDOS?
Anyone remembers? None.
Yeah.
Is there an H?
Minus your 12 over 2.
I guess. Yeah. Do you want me to just say
Minus
it?
I.
Yeah, George,
Okay. It'd be negative IH d by dx.
Okay, first derivative with respect to x. But if it's a square, then
Then d squared by dx squared.
second derivative with respect to the coordinate. Right?
Oh, you might write it.
So you will still have mass there. You will have 1/2 divided by m, right? And then second derivative with respect to the coordinate. Now the question is which coordinate? You said that this is a kinetic energy of what? Of electrons or a nuclei?
The nuclei, I believe.
Well, this is what you define your T, right? So if it's a kinetic energy of a nuclei, then which coordinate you will take as a derivative? Coordinate of electrons or coordinate of nuclei?
The coordinates of the nuclei.
Great.
And you can use any letter, but just declare it. Which letter would you like to use for coordinate of nuclei?
N.
Huh?
Well, N. 'Cause-
Okay, you are free to define whatever you like, but typically it is either X or R, and some people like R
Big R.
There you go.
uppercase. Okay.
Okay. So is there any more questions on the non-adiabatic coupling?
Oh, now it's crystal.
Crystal, please.
No. I have another one. What does the prime mean on the T? It looks like a prime from the blurry vision we have.
It's basically how they explained that was just it's taken into account 2 of them instead of 1. Nuclear, I guess.
You're so confident.
Yeah.
Levi?
Yes.
Don't believe him.
I have a hypothesis. I don't know the
wasn't-
source. But if Daniel was verbally declaring everything literally word by word, probably he told that it is quantum part of nuclear kinetic energy.
Oh, that's why it's prime. Right?
So you can, if you already know the classical trajectory, you can define overall momentum as expectation value plus quantum operator. And then you can split kinetic energy on contribution from classical mechanics and the contribution from quantum mechanics that will not change trajectory anymore, but will affect only like broadening.
Okay,
But
I
it is
guess
only
my
my
question.
guess.
My question deals with the if you conjugate 2 wave orbitals that are not the same as equal to 0. So wouldn't the second term be, if there's no time, 0? Because you would only have diagonal elements, which are is your first term in the expression?
The kinetic energy operator includes derivatives, as Daniel has introduced to us. And these derivatives will change functional form of the functions on the right side.
Left and right, that's why there will be not give you 0, right? Because
Okay.
you take a derivative,
Good.
actually second derivative, from your right, and then overlap with what you have on the left.
And another comment that it looks like Daniel presents us influence of non-adiabatic coupling onto time-independent states. So it is first-order perturbation theory giving corrections to the wave functions and energies, but not to dynamic processes. Therefore, this equation looks a little unusual for many of us.
Let's move on. Because we still have presentation from Japan.
So,
Which starts in 25 minutes.
alright, so is there any more questions on this?
We decided to
No,
move
we're
on
good.
independent on the questions.
Okay, so I guess another term to explain is a radiative recombination. And I guess from my understanding of this, it's whenever an electron moves from the conduction band over to, I guess, the empty valence band. Associated with that hole, an electron will emit its energy.
Always.
And it relax to that hole, correct?
Always.
Always?
Always. Independent on anything. So as soon as electron is on a luma and returns back to home, it always radiates. Everyone agrees.
9.
Really?
No.
Now it's your turn. Correct.
July didn't listen to the question.
Repeat your
I was
statement.
writing.
He was defining the radiative recombination.
I guess from my understanding, it's whenever an electron moves over from the conduction band to the empty valence band, associated with that hole, I guess the electron will emit its energy and relax into that hole.
It emits energy in form of light, in form of electromagnetic
From
field.
light.
Do you agree?
It's not true always.
Then how? Then correct. When is it not true? Or when is it true?
So there are a lot. It can relax to the whole in a lot of different way.
But what would be the
So-
condition when it really will emit light, when it returns to its home?
Their momentum should be
Which momentum?
sorry, transition dipole moment should be in,
Should be 0, 1, 10.
should be
Should be. Help us. Should be what?
Non-zero.
non-zero.
Non-zero. If it's 0, then it's
It
actually
is non-radiatively.
non-radiatively, and then there would be some other channels to
Mhm.
put your hole. So actually, it's not always true. When you can return back from wherever from your lowest unoccupied state, what you call conduction band, to the highest occupied state, H of the valence band, right?
Yeah.
You can do it radiatively or non-radiatively. Both mechanisms are possible. To have it radiatively, then you need to have a special property for your wave function of your Hom and Lumo, of your ages, states at the age of your valence and conduction band, so that if you use these orbitals and calculate your transition dipole moment, then it has to be not equal to 0. If it equals to 0, because of the symmetry of the wave functions, right, it can be 0, then it will be not radiative, and then there should be some other processes to be involved.
Okay. So I guess that also solves, well, an external non-radiative combination, but that's basically just the electron fits into the hole without any emission. So
Without emission of electromagnetic quantum,
yeah.
but energy must be conserved. Something
So
is
it lose energy anyway, in both cases, right?
Is-
The only question is, it lose energy in which form?
into which degree of freedom?
If it lose energy in electromagnetic wave, as electromagnetic wave needs light, right, then it's a need. If not, then it's not a need. But then it can lose it to the phonon vibration, for example, to heat.
All right, because well, I guess I sort of figured what the non-radiative electron just gives the energy freely away
Away to where?
to.
To whom? Again, we cannot just lose energy to nothing, right? Again, because of the conservation energy law.
Does it lose it to the hole that it occupies?
Well, energy of hole is low. So you lose energy, like difference, this is the loss of energy. So you cannot just lose it, it has to be taken by something. It's either taken by photon, this is your electromagnetic wave, right?
Okay,
And
yeah.
this is, you see as a shining light. Or it goes to heat, which again means it goes to vibrations. Your atoms, your nucleus starts move just more frequently, more rapidly.
Yes. Okay. So I guess I can move on to I guess more about the paper itself. I guess. Well, a quick little introduction to this is the whole point to the I guess the experiment was to find out the effects on the surface by two different types of perovskites. One where the surfaces contain a lead iodide-rich surface, and the other one where the surface is a more of a methylammonium iodide-rich system. So the difference between both of them is that, well, the methylammonium cations, they contain high frequency phonons, strong electric fields, and
Why is it high frequency phonons?
high electric, well, why is it high frequency phonons?
Yes.
Because I would say it's probably, well, yeah.
Well, I guess I can show you.
How the frequency of phonons will be affected by mass
Atomic mass of the
of the molecule?
of atoms involved in
Well, the
building.
methylammonium cations, they're much lighter
Uh-huh.
ion compared to the lead iodide.
Uh-huh.
So I guess the phonons.
But if we think about harmonic approximation,
Yeah.
right? So this is a kind of very valid approximation if you are close to the ground state, close to the equilibrium for your nuclear motion, right? So then how would the frequency depends on a
Mass.
well, on a mass, on a K, kind of, the hardness of your spring, or the type of the bond, the strength of the bond.
Force constant.
Mm-hmm.
Anyone remembers this formula? Usually people use the cyclic frequency, omega,
Omega.
equals.
Omega is equal to the square root of k over mu.
Said Levi looking in a Google. No?
No, I'm actually looking at the paper.
Oh, okay.
Your screen's frozen.
So it's a root square k over m, where m is your mass, right?
Yeah.
And k is a kind of, the strength of the bond. But now we go with this mass. The lighter, the smaller m, the higher the frequency, because it's a reverse proportional, right? Root square 1 over m.
Yeah.
So if you make your m very high, your f goes down and backward.
Oh, I guess I didn't really.
No? Does make sense?
Yeah, it makes sense. I just didn't really think about like the force constant, things like. I guess
Well,
I didn't zoom into
force
that.
constant, we even didn't really, for force constant, I don't know, it's a little bit harder. Well, you can think now about the strength of the bond between what boron, what you have, the
it's
lead iodine, or what is really moving in these vibrations. And your ammonia, which is nitrogen, I guess, is it connected with nitrogen?
It has hydrogens connected to the nitrogen, which is connected
No,
to
to the
methyl-
lead. Lead is coordinated with nitrogen probably, right?
Yeah.
Okay, so it's really probably this bond lead nitrogen versus lead iodine. So I don't know, K also might be different, and actually with K it's backward behavior. The stronger, the larger frequency. But probably mass is a main factor here.
Okay. Yeah, it said that. Well, I just assumed the lighter cations are more freely to move just because
But
they're
see,
lighter.
all the things is very easy if you really remember formulas from physics
Mm-hmm.
and quantum mechanics.
Yeah, I gotta go back and really review my homework on that. No, it's not a doubt, without a doubt on that.
One small comment on that. What is the second bullet? Is that phosphorus bromine iodine or lead iodide?
This one?
Mm.
Lead iodide. Oh, I'm sorry, I didn't put a lowercase.
Yeah,
I did that once. I think I did that a lot of times. So,
Phosphorus boron iodine.
if I did that here, I probably did it throughout the rest of the slides too.
I looked at the intro of the paper, and the high frequency modes are for the organic materials, not the entire lattice. I believe.
That's what it says here.
Which still
Yeah, you
valid
mentioned
Yeah.
metallic.
with your
Yeah.
mass, right? Because you have much lighter mass of ammonia comparing to iodine in a lattice. But
Right.
again, your molecules should be, they are not by themselves, they are connected through so coordinated with the lead. So you expect that your lattice kind of contribute to this normal mode as well. Just due to this bonding with the lead. So, continue.
I'll continue now. Okay, so the methylammonium cation rich surface also has strong electric fields, and this basically couples to charge carriers, so it makes it have stronger charge carrier interactions. Along with this system, they also have larger non-adiabatic coupling, and with the lead ion surface rich system, on non-adiabatic couplings, you actually see a drop by nearly an order of a magnitude, and it is theorized that because of this, of the reduced non-adiabatic coupling, the charge carrier lifetime is significantly improved due to some experimental results they've seen. And the system can also suppress the non-radiative charge carrier recombination, which is talked more about it thoroughly through the calculations they did, the molecular dynamics. And I can move on to, is there any more questions? I guess just a little quick introduction to this. So here, as I explained earlier, is the lead iodide rich system and the methylammonium iodide rich system, which just the surfaces are just highly concentrated compared one to the other. So here in the figures B and D.
Daniel, can I interrupt for a really silly question? What are those black diamonds?
What are those black diamonds?
What do they symbolize?
The perovskite structure at room temperature. It's the tetragonal structure.
But if some of us didn't have chemistry background, like how to interpret this diamonds?
I guess as a crystal lattice. Well, I guess in
So
the
you
shape
said
of
already,
it.
octahedral, each of these diamonds is your octahedral kind of structure, right?
Should I interpret like lead ion has this diamond shape? Tell literally how to interpret it.
How to interpret it? Well, I guess at the ends of each side would be the iodides on each of the ends. Well, I guess the lead would be in the middle.
Oh, okay, good.
So I guess it's just the shape of the bonds. I suppose with
So it simplifies. No,
So like in this sector,
lead in the middle,
an iodine in.
on the corners.
on the corners.
How many
Both
corners you have?
composition is the same, just surface is different, right? Composition of the both system is same, just surface is different.
Yeah, just the surfaces are.
No.
He's asking you about like how to explain.
For your C case, right? In these octahedral structures, what do you have? You still have iodine in your corners of
Yeah. The only thing that's different is the surfaces where we see the right here on the surfaces. So you see in the bottom.
It's not
and
on
the
the
top
surfaces; they're also in intermediate layers as well. Then where they are?
Yeah.
Yeah, so isn't it iodine on the corner of each diamond?
Yeah.
Yes.
Are you asking what's the difference between the two structures?
Yes.
Oh well, I guess you see at the ends, at the surfaces, at the bottom surface, the top surface, they have lead iodide. It's just the tetragonal structure cut in half, where where the lead iodide surface is exposed. So
So it's just different lattice. How
Different
they cut.
cut.
How they cut.
Same
the
surface, but like one is
Cut
cut
in
at the full unit cell and another at a half of unit cell.
So you have different termination. One is
Yes.
terminated by iodine, another is terminated by ammonia.
yeah. Okay.
Wow.
So
I was just curious what it is.
with the figures B and D, they took a partial density of states to see which I guess atoms or molecules are adding huge contributions to the density of states. So what they found was the methylammonium hardly had any or if contributions to the bands, while the lead had somewhat little contribution, while they saw the major player in the density of states was the iodine atom. So I guess they could just assume that the methylammonium doesn't really have a huge effect on the conduction band.
Daniel, major iodine is major contributor to valence band, but for conduction
But
band,
it's in both cases.
major contributor is lead, right?
Yeah, I'm sorry.
So your iodine contributing to the valence band, and it's kind of similar in both cases.
Yeah,
But for the conduction band,
conduction
unoccupied
band
states,
is lead. Yeah.
then it's lead, and is it still like both are dominated by lead, right?
Yeah.
Red is your lead.
Yeah.
But then what exactly is the difference you say?
The difference, well, I guess they just wanted to see whether, you know how since one surface, the lead iodide is more exposed and the methylammonium iodide is more significantly, more easily approached or attacked, I guess you could say.
Oh, the gap is larger for methylammonium rich.
Yeah.
Yeah, I was also going to point to that table too. The band gap is about almost half an EV bigger in the methylammonium system compared to the lead iodide system.
But ammonia doesn't really contribute
No.
directly. Or okay.
Yeah, the methylammonium doesn't really, yeah.
But
That's
conduction
what the
band is almost
test-
same in the both cases from the lead.
Really? You see red going shifted more.
I mean not conduction band, balance band. Balance band it doesn't shift anything, not even lead. Lead also in close to the frontier orbital.
Yeah. So it looks like it's mainly unoccupied states which really makes a difference.
Specifically, yeah.
So the methylammonium doesn't hybridize with frontier orbitals, but it changes
The gap.
the gap.
It opens a gap somehow.
So what they, I guess they sort of came under the conclusion of why there's a much smaller band gap is due to unsaturated chemical bonds that are present right there, and I guess they could theorize it as shallow trap states. Also, because of the smaller band gap, this should also accelerate radiative recombination rates. So that I'll explain that more in a little bit, I guess, in a couple slides where they actually did a little test on this to observe those rates. But I guess in when we go up to the table right there, they figured out how tau, which is the charge recombination rate, was pretty much found to be almost a magnitude bigger than the methylammonium iodide. And the NAC, or the non-adiabatic couplate, was also found to be basically almost a whole magnitude bigger in the methylammonium iodide rich system. However, I guess in this case where they considered pure dephasing time as a term, but I guess they used it to explain it as quantum coherence. I didn't really understand what that term meant, but like I guess coherent meant like how you understand something.
I forgot, was it Brandon or was it Levi who was presenting it last, when
Year.
it was in April? It was spring.
It was me.
Or fall, I don't remember. It was Levi?
Yes.
So can you help with definitions then?
Quantum coherence.
Decoherence. So if you think about a cosine wave, right?
Yeah.
It starts out at the maximum and then it goes down and then it goes up and so forth, right? So quantum mechanically, you can use that and sine where sine rapidly oscillates, which means if you multiply the rapidly oscillating sine by the cosine, it does like an envelope function. And when the envelope function goes to 0, you're out of phase completely. And since the system can't get back into phase, we don't really care about the rest of it going back up. We just care that it drops to 0. And that is if you kind of, so the cosine itself is like the external thing, where the sine, those are kind of the ways to measure how the system evolves in time, which means that they start to get out of phase, and then once they're out of phase, they're done. I know that's terrible, but that's all I remember right now.
Yeah.
And Daniel, you can tell to all of us.
Oh, yeah.
According to definition by Levi, I am continuing.
Yeah. Thanks for that nice explanation.
Little explanation.
Based on Levi's explanation, they made a graph. The quantum decoherence. And due to that, they found out it's basically similar. So between these two systems, there wasn't too much of an effect on the quantum coherence. But they fit it to this Gaussian, this exponential decay, where they took the charge combination rate divided by the dephasing time squared. Then they took half of that exponential, and they got this graph. So the big picture from that is that quantum coherence is not really a major player in these two systems. So with this one, this graph is based off of the charge carrier recombination rates, or the decay of the excited state population. So you see that the charge carrier recombination rate of the methylammonium iodide is only lasts about 3.5 seconds, compared to the lead iodide rich system that lasted almost a whole magnitude bigger.
It's population of which state?
The excited state.
And where do they excite?
Or it is lowest excited state.
The lowest excited state? It probably would have been the lowest excited state. I didn't really think about that. I guess which excited state would it be then? Because I guess there's many of them.
Well, since it goes only less than % within 10 picosecond, it's very likely that it is lowest excited state. And when you were presenting the introduction, you made an accent on recombination, radiative and non-radiative, which means from the lowest excitation.
Okay, yeah. Lowest.
Can you go back to the density of states?
Oh, I see it too. You should send it to him. So I'm confused.
And finger, where is the lowest excitation?
Where's the lowest excite?
Yes, from where to where?
Where to where?
Yeah, electron from where to where is excited to form a lowest excitation.
Wouldn't it just be from the bands?
From
Ages.
From the top of the valence band to where?
to the top of the conduction bank?
Yeah, yeah, perfect.
Top of the conduction band or
So
lowest
they,
conduction
they
band?
look on the
Bottom of the conduction.
kind of your first excited state, right? From common to lumen, in other words.
It's problematic to
And then
define
they look
top
on
of
the
it.
returning back,
No, that's-
a
I have that
recombination,
too.
right? So it's not really relaxation. They're not going from one electronic level to another in a band. They go through the gap, right? So that's why it's called recombination. Moving.
You don't want to be nice.
That John with us or he lost
So
connection?
I was just wondering if anybody else had any more questions on this one. I guess there's the equation of the Gaussian they fitted to as well.
For the stepwise population change in the A panel, did they correlate that to any specific motion in the material? Because it looks like it's about 2 picoseconds per step.
I'm sorry, what was the question again? Did you say like to which structure or?
No. Please repeat the question. It's very interesting question.
Yep. So in your A panel,
Did you
you
get
can
it?
see that the population looks like, a set of steps.
Yeah.
And so from one step to the next, it looks like it's close to 2 picoseconds on their time scale. Did they say anything about why there were these types of steps? Was there a specific motion from, a given atom that correlates to that?
I don't think they mentioned something like that. Because I guess they just sort of took it back to where
Did you get it?
where they basically just said it was due to the non-adiabatic coupling rates that you see that the lower non-adiabatic value that the lead iodide rich system is emitting is the explanation for why there is such a huge difference between both graphs.
Daniel,
Yeah.
can I contribute and extend the question of John?
Yeah.
So, in few next slides, you may show how non-adiabatic couplings depend on time. So they're not time independent. And maybe the change in time of, first, non-adiabatic couplings, and second, the occupation of lowest excitation are dictated by repeating pattern of molecular motion. Maybe it is contraction of some specific bond. Maybe it is a rotation of methylammonium as a whole object. But John is asking authors of the paper, through you as their representative,
Yeah.
which atomic motion is responsible for this interesting feature that it is not a straight line, but it goes through the steps, and steps are have the same pattern, same duration, approximately 2 picosecond long.
Oh yeah, you're talking about like the little, quick drops thing.
Yes, quick drops.
Steps.
So the question is about quick drops and origin of these quick drops. John, am I representing you right?
Yeah, that's correct.
Okay.
It looks like they didn't discuss it.
Not too much. They just blamed it on the non-adiabatic
So
coupling.
then, if it's still under review,
It's
this would be a question to ask for the authors.
okay.
Who's writing review? He?
Let's not disclose.
Okay, so this is the time-dependent absolute non-adiabatic coupling chart of the two systems. So in red is the methylammonium iodide, and if you could barely see the lead iodide rich system, you see that methylammonium iodide has a huger contribution than the lead iodide, which is nearly basically non-present in the graph. So what they blamed this huge, or not blamed, but rationalized this huge difference is the non-adiabatic coupling fluctuated a lot due to, I guess, the proportional to the nuclear velocity. So they said that the velocity of the lead iodide system played a huge part in the fact that you see such a huge discrepancy with the lead iodide system, which was barely existent, if all.
But which one again fluctuates? Red or black? Or they kind of fluctuate simultaneously?
Well, I
in
guess
the same way.
I guess they blame the fact that well, you know how you see basically the methylammonium iodide overwhelms the lead iodide, you barely see.
Daniel, is there a contradiction in how you present the story or in what they write? So in the table and rational explanation, you are telling that lead-rich surface has unsaturated bond, therefore it gives quicker relaxation. Or I misinterpreted. And here you show that lead-rich is like order of magnitude lower non-adiabatic coupling.
Yeah.
Were you saying so?
Yeah, I said that.
Is it in the contradiction? Like if the non-adiabatic coupling is smaller, then transitions should be slower.
Yeah, that's sort of why I presented this paper today instead of Tuesday, because the paper just kind of contradicted itself many times, so I kind of had a hard time.
But are you sure this is exactly the statement? Like again, if you return back to your table, not to your their table, to the table on non-adiabatic couplings, right? So you're saying that which of these couplings are larger?
The methylammonium system.
It's the larger couplings.
Yes, by almost 9 times bigger.
Okay, and they also overlap. Then there's no contradiction. Why is it contradiction?
So coupling larger 10 times, and
Yes.
and lifetime is shorter.
Yeah, the lifetime is
Okay,
shorter.
then it's no contradiction. It agrees with itself. Okay.
Because again, coupling is proportional to the jumps, to your jump from highest to lowest state, right?
Yeah.
So the larger the coupling, the quicker it jumps. The larger the probability that it jumps, right? Which means it should be quicker with a higher probability.
Yeah.
So no contradiction.
Would you permit me to approach your screen and point something?
You go absolutely.
John, do you see the screen as it transmitted?
He should see the paper, which was
No,
sent.
here.
Yeah, well, I see the screen and I have the paper pulled open right now.
Okay, so the black features oscillate less vividly than red features, and they appear like maximum, then nothing, then maximum, then again nothing, with regularity that may correspond to this 2 picosecond.
Well, I was going to say there's a panel C of this figure that has the wave numbers for the phonon frequencies. So if he has that in the next slide, yep, this one.
So?
Oh, okay. So the difference between these two is that the methylammonium iodide, well, this is a phonon influence spectra. You see that the methylammonium iodide system, which is the one in red, has higher frequency phonons compared to, I guess, the lower frequency phonons that are exhibited by the lead iodide system. And so I guess this is why you see the huge fluctuations of the NAC values. Okay.
Daniel, from your chemical background and experience, what is the frequency of carbon to nitrogen stretch, carbon to nitrogen bond oscillation in inverse centimeters?
Inverse centimeters?
I know carbon-carbon.
So what it is?
1,500 right now.
So they're not showing the right range.
I guess because their range is dictated by the lead, iodine, or maybe lead ammonia.
So the stretches between carbon and nitrogen do not contribute to couplings?
Not at this range. It should be much higher.
No, you would have to extend this up to like 2,000 wave numbers to even look at any of those.
Yeah.
But reviewer may ask authors to show it.
Or it might be not really contributing to the couplings with this, because again, this is just for the HOMO-LUMA transition, right? To your ground, to your first exciter to the ground state, and not necessarily that this transition is really coupled to your very high intensity phonons. Possible, which is possible, because if it would, then it probably would be non-radiative. Is it radiative transition, by the way? Do they say anything about it?
Radiative transmission?
Transition.
For which just yes.
Well, this slow transition, your HOMO-LUMA transition. Like they excite and then it returns back, right? But is it supposed, like they said, like it's radiative, non-radiative recombination.
Yeah.
So which way it goes? Through radiative recombination or through not radiative recombination?
They just kept saying non-radiative for
Okay.
the lead iodide system.
For both structures.
Well, I guess if they said they compared it things that lead iodide suppresses non-radiative recombination compared to, I guess, yeah.
So they do not give
Oh,
numbers
that's
for,
quite a lot.
for radiative channel.
Yeah.
So they assume that radiative channel takes much longer.
I assume, yeah, I think that's the approach they
Return
took.
back to the previous slide, even two previous, where you have population. Yeah, what do you mean longer? 23 nanoseconds? So this is in the range of radiative
Yes.
time, same as 3 nanoseconds.
So
No,
do they say
one-
explicitly if they neglect or take into account radiative channel?
Well, again, in your initial kind of introduction part, right, you were talking about radiative and non-radiative
Yeah.
recombination. But do they in the paper really make any conclusion? So what kind of recombinations they have here in the structures? Radiative or non-radiative? Or maybe one is more and other is less, I don't know.
Think-
What kind of evidence does they provide?
Well, the fact that what they stated with the lead iodide system, that it suppresses non-radiative, and then doesn't the radiative and non-radiative, don't they just compete with each other? So if you suppress one, wouldn't the other one happen? Is that how that works? Or not really?
Radiative seems, well, I can be wrong, but it seems to be independent of non-radiative.
They don't compete with each other?
Well, they do compete, even if
They,
they're not
they
dependent.
compete in a sense like radiative is all, let's say, always the same, and non-radiative may withdraw part of the erection channel from radiative.
In one sentence, they justify the higher recombination rate for methyl ammonium by saying that when the methyl ammonium on the surface, since it's a lighter atom, its motion is higher than compared to lead, and which can change the dipole moment. Transition dipole.
But they do not report transition dipole, neither spectrum.
They didn't say transition dipole, they're just saying that it will change the dipole, which will increase the electron and hole recombination rate.
Okay, so they provide hand waving outline.
Like,
So I guess this part is when it comes to the motions. So I guess this is more about, this kind of relates to the slide back here. Well, the slide right here to compare to, I guess, to be able to see the higher fluctuations of the non-adiabatic couplings were results of these type of motions that were caused by dimethylammonium iodines. The curved arrows demonstrates how the rotation, and well, they justified the higher NIC values due to the fact that some of these methylammonium ions, whenever they saw, I guess, the molecular dynamics more clearly than these images would show, they saw that the methylammonium ions would rotate into the cages that were with the perovskite structure. So they would rotate inside there, and due to that, you would see these higher NAC values. And so these were snapshots of how these methylammonium ions inside the cages would rotate and cause.
So again, if you go back to your frequencies for this previous, I think it's this, no, next one, this frequency kind of chart.
Oh,
So it's
has
they.
that.
It looks like we don't have really stretching for the CN or any stretching, but they refer to the rotational or maybe bending characteristics.
What's the period of rotation? Do they report? Like how long would it take for carbon and nitrogen part of methyl ammonium to swap their order?
Well, it looks like they're already showing this times, right? 2000.
No,
On the-
no,
on
no,
the
no,
figure.
no.
Well,
It
No,
shows
no, it shows that it
snapshots from-
rotates, right? The snapshot showing that it rotates by 90 degrees or so, no? Like your nitrogen is on the right at 2000 to 2.2 picosecond, right?
Yeah.
Uh-huh.
And then it goes to the almost lab.
No,
not almost
no,
lab.
it just turns a little bit.
It's a little bit like 30 degrees if.
But it turns by 30 degrees
Com-
after
com-
some
complete
time.
rotation would take maybe like
like 3 picoseconds or something like that, 3 to 5.
yes.
Well, you can have rotation along, like the
Which again, if you remember the
above
steps,
and
if you say
rotation
it's
above
about
Oh, liberation, not the complete rotation, but
just 30 degrees back like this, right? Something like this. Not this, but just in one plane. But also, by the way, this time scale.
precession around
Yeah.
the axis.
You could have that one too. That might be the one they're trying to.
But the time, if you kind of saying it's around, if this type of the rotational kind of motion is around 2-3 picosecond, again, this might be connected to these steps in a population which also having this periodicity with around 2 picosecond time scale, right?
So did they mention any rotational difference, the methyl ammonium inside the system and surface?
Can it mention anything between what the both
Or is
surfaces?
it, or both can rotate at the same way, or same degree of freedom there?
Well, what do you mean by that?
The methyl ammonium inside
Yeah.
the cluster, inside the pulse guide, and surface the pulse guide. Is there any difference on the rotation?
There should. If there is, it's basically it's slight. It's not as vivid as it is inside the structures.
It is
what
pretty-
they said.
But from the arrow, seems like they may say it's showing
That it
maybe
translates
similar.
on the surface.
Trans-
That's what the up. That's what I assume the up arrow means. Translation. But
Now, up arrow is there any total dipole showing presenting?
well, let's read this script. Curved and straight arrows indicate rotation and. Can't see the other word.
Let me know in the
in this
paper.
presentation.
In upward movement respectively. But the arrow length is the longer and smaller, is that indicating that upward movement is different in this each. How many methyl ammonium in the both system? Is the number of methyl ammonium the same number of methyl ammonium
In what?
in your both system?
On both systems? No, it's not. Because with the Axis lead iodide system right there, you see that there won't be the concentration of methyl ammonium iodides is decreased compared to, I guess, the methyl ammonium
Yeah.
iodide
Oh, one
has
layer.
more. There's a
okay.
huge
But
concentration.
most systems are stoichiometric.
Yes.
Struggling, okay. Makes-
But you have more ammonia in the ammonia case.
Yeah.
I guess that's why it's called ammonia. Are we close to conclusions?
Yeah, I got 2 more slides after that, but
Well, for
They're
first slide, we
conclusions,
spent half an hour.
So, but am I right? Like again, they claim that it's this rotational motion of ammonia when you have ammonia terminated case, ammonia rich case, then this kind of a dominate contribution to your frequencies, which results on this large coupling, which kind of leads to these large couplings.
yeah, it is because of the, well, you said because of the terminations?
Well, I mean, your ammonia rich versus iodine rich.
Yeah. So,
So it means if you have iodine rich and ammonia not really on the surface, then this rotation's kind of not as efficient and results on a smaller couplings.
yes, essentially. So, little quick remarks on this. So, they blame, so not that they blame, but they rationalize the non-adiabatic coupling is the main factor for the lower non-adiabatic coupling is the reason why the lead iodide system is the rich one is compared to be a more a better choice.
Can you
photovoltaic
explain
properties.
how this non-abiotic couplings really relates to the properties for the photovoltaics? What exactly, like some people might not even see the connection.
I didn't see
Like,
that
first of
connection
all-
either. That's why I was
But
like,
you're presenting,
yeah.
right? So at least you should have some ideas.
Yeah.
So what exactly, like you're saying the smaller, or like, first of all, is it like you should have small non-abiotic couplings to be beneficial for photovoltaics or backward?
It should be backwards, is what I always assumed.
So it should be large non-abiotic couplings.
Yes. That's also that's in the next part of my slides of where I had concerns.
But I think again, here is back. Again, which one is quicker, ammonia or iodine-rich case?
For relaxation rates, it would be the methylammonium system. It
And the
relaxes
couplings
faster.
are larger also for which of them?
The methylammonium iodide, everything's larger than methylammonium
So
system.
you have larger couplings for ammonia-rich system, right? And now just read your sentences here.
The non-adiabatic coupling is the main factor in
Rationalize the improved properties for iodine case,
Mhm.
which has smaller couplings.
Yeah.
So then your previous statement when I asked you the question is definitely wrong, just based on the observations. Because if you believe them 100%, then you can say, well, because they say that non-abiotic couplings factor for improved properties, and we know non-abiotic couplings are smaller for these iodine-rich cases, right? And it's improved properties. So then it means that small couplings, non-abiotic couplings, is really beneficial for the solar cell applications.
Yeah. Well, because I
Not
took,
large, but small.
No.
Now we need to explain why, give some physical reasoning for this.
Well, because I was just always under the assumption that the higher non-adiabatic coupling would result in better.
Okay,
result in
what is
better,
needed for
materials.
photovoltaics? What is a material when you call it's a good for photovoltaics? What is it doing actually? So you shine light, you're excited, right? And then what's happening?
It gives off energy. Well,
Of energy to what? Which energy to which energy? Again, we cannot just lose energy to nothing
yeah.
because of the conservation law. It just transfers from one type of energy to another type of energy. So it's not just loss of energy. It's loss energy to which energy again?
Ask how from what?
Maybe not loss, but transfer
Yeah, transfer.
of your solar energy, because you use the energy of sun
Yeah.
in photovoltaics. At least this is the reason to make these devices. You use the
Of
energy of
course, yes.
sun and convert it to what?
To electrons, I guess.
Very close. Just to standing electrons.
Change the last bit of the word.
Change the last bit of the word. To
What electrons have to do?
electrons, they provide electricity.
And for this they have to probably move. Moving electrons,
Yeah.
this is your current.
Moving.
If they just don't move, it's not a current,
In
right?
space, move in space, not in energy, not change their energy, but move in space.
Well, they kind of change their kinetic energy.
Going back to
So they need to move
Yeah.
in space from left side to right side or something like that, right? So, okay, good. Now, you excite, and you have now electron here. To make a current, it has to move. What if it doesn't move? If it returns back to the ground state? Would you have an efficient photovoltaic device?
No, it'd be the opposite of what you want, right?
So, but your non-abiotic couplings, at least here, right, telling you actually how quickly you return back to the ground state. If it returns very quickly to the ground state, then it doesn't have enough time to really do something else, to really move to the contacts and create the current. So that's why you want this to be very slow.
Can you go back to the density of states? I'll add something and then you will continue your explanation. So in this paper, you are considering recombination,
Recombination.
right?
Yeah.
via non-adiabatic couplings over the gap. Right? But in addition, one can consider non-adiabatic cooling. Cool here, cool there. If the electrons and holes were excited higher up, and this part of relaxation is good, potentially good for photovoltaic application.
Depends.
Depends.
If you want to use
Depends. It could be good, but this part of non-adiabatic relaxation is always bad for photovoltaic application. So the same process, but applied to different ranges of electronic states.
Because again, if you excite and then it returns immediately back to the ground state, you lose everything, right? So you just excite for nothing.
Yeah.
So you need really to have a good time so that your excited electron lives there in this state as long as possible, so it will have enough time to move somewhere else.
Okay, yeah. Guess thank you for clearing that up. I was kind of.
And this is exactly what they see with lead iodine-enriched surfaces, iodine-enriched cases, right? So like 10 times, roughly speaking, 23 versus whatever, 3.
Yeah.
Another second, so you have about 10 times, roughly, around 10 times slow recombination for the iodine case rather than for ammonia case. Which of course makes it to be better for the photovoltaics due to these processes. So you're just having your excited state to live much longer. So it has enough time to do something else.
Oh, okay.
And
yeah.
be converted to the current.
Oh, all right. Yeah. Okay. Yeah. So, yeah, I guess that kind of covers up the second line too. So with the increased non-adiabatic couplings in the methyl ammonium system, there was just stronger electron-proton interactions caused by the rotating methyl ammonium cations. The decreased non-adiabatic coupling suppresses the non-radiative electron-hole recombination. The electron energy gap is smaller in the lead iodide system. Due to this effect, it has an opposite effect on charge carrier reaction or reduction. Quantum coherence is essentially the same from both cases. That one doesn't really matter. My last and final slide. So something that I guess is that I was wondering, it goes sort of back to what you tied in. So I guess the rate of non-radiative electron hole recombination depends on these three subjects, right? The energy gap, quantum coherence, and the non-adiabatic coupling. So if that's the case, how come they state that the lead iodide system is the better systems? I guess I was just figuring out, but I think you may have solved that out for me due to the excited state population. That was probably one of my concerns I had when I was reading it.
Okay, at least one point was more or less resolved.
Yeah.
But I think we still anyone wants to add something about discussion on quantum coherence? Anyone have better ideas? I mean, sorry, Levi, a little bit better explanations than Levi has just presented about 1 hour ago.
I mean, it kind of tells you how long you can actually say anything with any sort of like.
Great, stop. This tells you how much you can say something with any sort of something.
I don't know how to word it, I guess, but like like once you can't say anything with any sort of certainty at all anymore, then you've lost your coherence, I guess, is kind of is where I'm trying to go with it. I don't know how to explain it any better.
Coherence is like the reliability of the system? Or?
Reliability on what?
As my when two-way propagate, they're losing their phase difference. How fast is that is coherence?
Phase difference in a wave function.
In
right?
a wave
You're
function,
talking about wave function, which has, we know, should have a phase kind of component, I5 or whatever, in a wave function. And so this phase can be lost at some time due to the, mainly in this case, due to the interaction with environment, right, or with nearest neighbors in a system. Okay.
So how fast is losing the phase known as a decoherence here?
Okay.
So if it losing the phase decoherence, that means usually it will relax faster. Or you will get some idea about decoherence from the shape of the adsorption curve.
You mean line widths?
Line width, yeah, I mean, should be a
Probably
line width.
for. I'd say not quite, maybe
broader
for
line width.
emission, maybe.
Oh, emission.
If you're
Yeah,
talking
yeah,
about the whole state.
emission. Broader line width means it's losing the coherency slowly. Coherence is fast, longer. Decoherence time is longer. Sorry, like that. Decoherence time is shorter if line width is longer.
Yeah, so decoherence happens quicker. If line
Quicker.
width is wider.
Wider, sorry, yeah.
Okay. Anyone else?
Any final
Maybe
thoughts?
Brandon.
Questions?
Or maybe John. Regarding decoherence.
I would say I think of it similar to the way Jabed described it, because you could look at, a singular wave peak and have two of them overlapping. And as you're going to move through time, the phase might shift. And so now they're at different positions, but they're also going to shape differently. So when they're on top of each other, the overlap, if you want to think about it, provides the coherence. And once you start stretching it out, the probabilities are no longer having a very strong overlap, so the coherence is lost. At least that's the way I think about it.
Okay. Are we ready?
Yeah, any
For-
final
for-
thoughts?
We are ready to
Uploading.
upload. Let's finish.
So it was, I guess, fruitful
And the
discussion.
second half of
Yeah.
our meeting.
Thank you.
Now
Thank
you
you.
have to go very
I have a lot of
quickly.
homework
Only
to do.
30
Yeah.
minutes.
I guess we could make it better.
Looking at a smile, Daniel likes to present.
Yeah, it helps me know that that I have a lot to work on. So
But I hope it was really not very boring because I don't know, it was not boring for me. Maybe because I was talking mostly.
Alice is not here.
Oh, she's busy today with.
She missed this.
Yeah, but she was helping the incoming students to learn something about NTSU.
You guys can't see us moving, right? Like we're totally still and John's totally still. Is that true?
Yes.
Yeah, your face hasn't moved for half an hour.
Yeah, you
Oh,
frozen.
okay.
But we can hear you at least this time.
Thank you.
Okay, that's good.
It's a trade-off.
Can we maybe do something so they will be unfrozen?
Let's try. Well, let's Jabed load his thing, and then we'll try something to unfreeze.
We can try and sign out and sign back in.
But it's not us because John's also frozen.
Maybe it's too much radical.
Oh, it's sorry, yeah.
That would take like.
This one?
Oh, where's that?
Sorry, PowerPoint kind of.
Let me download it on the desktop.
Still doesn't work?
Why is showing the user? Oh. Can I?
And on coming Tuesday, we'll have a set of several mini presentations. If you look online for the Google Docs document, you'll see the list of self-volunteers or assigned talks. So look on it now if you like or dislike it.
Did you want me to go on Tuesday? Was that?
Everyone, no. You will go one Tuesday 10 minutes among big group, and another Tuesday, the whole day will be yours when you will do update on your research project.
Okay.
Coming Tuesday, we will cover only basic skills for getting through the electron dynamics. It will be not update on personal research projects.
Okay, so you just want me to talk about like how to
Yes,
whatever is
just
best.
steps, crash course over electron dynamics, non-adiabatic couplings, and such.
Okay.
Just technical.
Yes, just technical.
Okay, thank you guys for, and my presentation would be.
Oh, should we try to bring back?
Oh, sure.
To make them alive?
No, nothing.
Back. Screen.
Maybe
Does it
it
mean
may,
that
it,
the
Levi
Connected?
told that he wants to
it may
log in
things
again.
worse.
We lost them.
Okay, we'll send them recordings.
We're still here.
But the problem is that now we don't see you at all. We have just a black screen.
It's better this
Yeah, that's not. Is that terrible?
It's not terrible. It's just before we at least saw your faces.
It was a,
Now it's no faces at all. But we can hear you.
Well, now we
guess
can't see you.
You need to
Brandon.
speak so we know what's going on.
Brendan's messing on our side, so now we can not see you guys.
Oh, no, this wasn't me.
That one's not him.
This one wasn't me. I can control what we see from this. That's it.
Oh, what? Get them back up.
Do you guys want to re-log in again?
I'm saying I
log out,
can't.
log in?
You can't?
Them.
Oh
That is
no.
them.
Oh, that's them.
Sure.
No, but they're up there.
So how do we switch these?
I don't know. You're the one messing with it.
Did you try to switch on and then switch off again? Switch off and then switch on again?
No, we can do that.
Disconnect.
Here, let's.
Okay, let's disconnect.
Maybe it was not a good idea.
Everything is blacked
Oh,
out.
it's still there.
no video.
Did it update anything?
No.
No.
We still can
Okay.
hear but don't see you.
I would
Turn off your TV.
I would suggest us to just go because I think Javed only has like 25 minutes.
But did you try the power on the other TV? Is that off?
No, it's frozen.
Okay.
Okay, let's go.
Yeah, I guess it would be better. Just it's okay. So
Just cry when
Yeah.
you really want to ask the question.
Okay.
Scream.
Scream. Yell. Holla.
okay, I guess my talk will be shorter compared to the one which we reported to, because I'm gonna show some experimental results and with how they compare with some calculations to try to predict the structure of the silver atoms. I didn't put any introduction in this talk because all of us know that silver cluster. Oh, it just sound okay. So the difficulties of the silver cluster is very unstable when we ligate it with DNA. So in that case, we cannot do any experimental evidence to get a cluster because using like X-ray diffraction experiment or such other kinds. So this is one of the biggest challenges to explore the structure of it.
So why you cannot use just X-ray spectroscopy?
Because when the DNA ligate is not that much stable in that case. If we apply the high energy like X-ray, it will be a cluster become diffused or bond between the silver and DNA is not strong enough to do this one. And also, especially in the DNA cases, when we synthesize the silver cluster by using the DNA, they don't have a specific crystal structure. So it's very hard to get the structure one. So most of the time, I would say almost every time when I look through the literature, I found that they try to get the charge and the overall sizes of the cluster, and they hypothesize some matter and some shape and do some calculations and compare their calculation and experimental calculation with hypothesis. So try to figure out the shape indirectly to matching their result and hypothesis. So I'm going to talk with the basically two papers, mainly on the first one. Both of them also followed the same rules, and they do some experiment results about the size and shape and the absorption spectra, and they hypothesize the some structure. They do some calculations and they match their result and to predict their ultimate structure of the dots. Another important thing is in this both of them we are talking about the DNA ligated, because DNA ligated silver cluster is very unstable compared to the other one like anionic passivations. In most of the cases, anionic passivations, they got a strong, bigger means like 20 to 24 different size of cluster, and they are able to do some certain experiment to figure out the shape. But in this DNA cases, it's also more uncertain in this case. So both of them, they use the DNA defines different nucleotide. I'm not going to talk about the composition of nucleotide. They're saying that we know that the shape and emission properties depends on the...
Which year of this journal?
This one is 2013 and this one is 2015, I believe. I forget the exact year. Oh, sorry, I have.
Well, is there a reason why?
Yeah, 13 and 16, 2016. This one is 2016. So, so this one is a pretty common one in every case. I'm just showing you from the both of them. As I said, they do the mass spectrum sometimes, and then from the mass spectrum, they will get overall idea about the shape of the cluster and the charge. In these cases, they will get this mass spectrum and each peak because of different oxidation state, and by doing some calculations, because suppose like so the gap between the each peak is indicating the oxidation state difference in this case. And now if we equivalent these equations, the overall charge with overall charge of the system, when the charge class positive cationic silver bonded with the DNA will dehybridized, they loses one hydrogen and they form a bond. So overall charge of the system should be the balance of the hybridizations and the total charge of the system, and then it will give you the overall charge, and this gap is the overall charge of the system.
Can you please help to interpret the experimental spectra?
I mean,
no, just where you were.
Yeah, I don't know how it is. Let me use the keyboard.
Yes, so this rightmost panel, you do have about between 1,500 and 2,000 two clusters, at least two more.
Yeah.
One with 5 silvers and another is with 17. Can they be so close in their mass? Can you interpret how different charge affects on position of the cluster of the different mass on this axis?
So this charge, this charge is it's representing the overall charge. Overall means silver cluster with the DNA. So its position is, this one is charge difference because of a different ligand here. So they kind of synthesize the bunch of in solution medium and took this absorption mass spectrum. So
should we take the please finger on the highest peak.
This page.
Yes. So should we, and on the bottom of this where it intersects? No, the highest peak intersects the x-axis. The value lower.
The value of
Yes.
the
It's like around 1300.
Okay, 1300. Should we multiply this 1300 by 3 to get the actual mass of the cluster? Because the charge is 3 minus.
Yeah.
Can you explain it once again and check that everyone understands it? So your x-axis is mass divided by charge.
So, not the multiplied by 3. I would say the difference between the x should be 3. But that difference will be give you the charge if the ligands and mass everything is same. So this one is showing the -1, this is a +3, but maybe your question is why is like 200?
They're almost the same mass, but 17 atoms of silver should be about 3 times heavier.
That's not the same mass because ligand is different. They have 11, suppose like in this one they have a 12 ligand, this one is a 6 ligand only. Sorry, see? Yeah, 6 ligand. So
Hey, Javed?
this ligand is
Javed?
yeah.
I think Dimitri is correct, because if you look at the position that is -3, if you take about half of that and you add it to it, that's about the position that says -2. Right?
-3 or -1?
Question?
I think he's trying to point out the AG
Yes,
17.
so
now,
actually
wasn't
so
it?
just
So-
has a
He's an expert.
expert in mass spectrum, so he should.
So the horizontal axis is just the mass to charge ratio.
Yeah.
So to get the right mass, you need to multiply the charge of your species.
Multiply the value on the x-axis on the charge of the species.
Right.
So if it shows 1,300, then and the charge is 2 minus, then the actual mass of this fragment will be 3,900. Okay.
Oh. Okay, that makes sense. Okay, I don't know much about the mass spectrum, so yeah.
But this mass correlates to just silver or together with the DNA?
This mass is correlated with the whole
The entire system.
Yes.
But then how they can figure out that it's 17 silvers there? Because their DNA is huge.
Because they know the DNA, which DNA they use.
Oh, they know exactly the
Exactly, yeah, because
and the length, so they can
yeah,
figure. Like they know
composition.
for sure what the mass
Mass
of
of
DNA,
DNA, yeah.
and based on this, they can figure out what is the number of atoms. Okay.
Yeah. So in these cases, they use the single DNA, I mean specific DNA, and so they got the different mass should be different, same, but this splitting is indicating the charge of the oxidation state difference of this cluster system. And yeah. So they do some balancing with these equations, and then if we plot the different oxidation state, it will move to the different way. But this system is matched with the experimental result. From that, they decided what is the oxidation state of the system by matching this whole different methods.
And this is the numbers correlated into this other
This
plot.
is not the
Or
correct. I
they
just
not-
give you some 2 examples because there's a pretty common technique in all cases to get the mass spectrum. So this is the taken from these two these two papers I just showed you. The first one is taken from the 2013 paper one, and second one is taken from the 2016 paper one. So this is most of the experimental feature actually. So from there they got an idea about the cluster, cluster charge. But now main challenge is to predict what would be the shape of the cluster charge. As I told you from the before, they did not do any specific calculations to predict the shape. But in this case, they do something like first one. Let me explain the figure first. This black and this all red means they synthesize the cluster by using a single strand DNA, and these green are synthesized by using the double-strand DNA. And solid triangle here in the both sides is indicating they are emissive, and other one is empty one is indicating their dark silver cluster. They are not emissive.
So only triangles, this is the structures which emit light. Which do
solid triangle,
Solid triangle. So can you guide us and tell like which numbers are emissive?
Just a few examples.
Like 13,
Okay.
14, 15.
And smallest one?
And if you go to smaller,
seven?
they're not.
7 and
So
8?
smaller, they are not emissive here.
No, but 9?
Yeah, 9 is emissive.
9,
and
10,
10 or 11, I guess, yeah.
And then the next one, there is no 12, there is only 13.
No, yeah, only 13.
13.
But this is based on what?
This
on models or on experiment?
The size and charge is based on their mass spectrum.
Okay.
From previous show in this one, I just showed
So
this one.
actually, these symbols they completely correlate with experiment.
Experiment, yeah.
It's just taken from experiment. Okay.
So they're trying to see what is the relation between the over size of the cluster and charge of the cluster. Oxidation state of the cluster. Is there have any correlations between them? One.
But they all are rods. They're not spherical, they are continuous rods.
They don't know yet.
They don't know yet.
Hypothesis, the legend.
No, let him finish.
Yeah.
I guess
Okay.
he will go to this point.
So then, as you said, they try to hypothesize the different shape of the rod to compensate the total charge of the system.
But before you go, why they start with the rods in the first place? Why they cannot imagine that should be a cluster, compact, spherical, or
yeah, they discuss. I'm just going to discuss they discuss in the whole literature. It's kind of like, I would say, elimination methods. They compare their result with all other possibilities. They shouldn't match they didn't match with the experiment. But this method,
like if they consider rods, then they match.
Consider, yeah. But rod also can form in a different way because it's a fixed nucleotides. So their conformation of the nucleotide is fixed. So how can they compensate the different number of charges? First, if you look at the suppose like less than 9 cluster, the charge and the size ratio almost close to the 1. So that means this is the fully oxidized. All silver atoms are oxidized here, 1 silver plus more. And in that case, they're saying that it can give you the 1 plus, all silver are oxidized if you get something like this one. So this one is indicating that like all silver atoms bonded with the nucleotides, and that nucleotide also hybridized. So it can get bond like 4 or 5 silver plus. But in this case, there were some other cases. This pink line this ratio is around 0.67. Their calculations. So if you like, a lot of cluster is lying on this line. So in this one, if you wanna compensate that much charge, you need to get something like this one. So in this case, because this surface silver, these are oxidized, but in the center, these are neutral silver atoms. So you need to get something like this one. And if you look at this figure, it's showing one of the such a system. This and the base pair between the single strand DNA are Watson-Crick type, like the regular one, which one. And they bonded with the silver, and then in the middle row, this is the neutral silver, gray color one, and blue color is indicating that this charged silver. So if you imagine this kind of conformations, you can place around 0.67 ratio of charged clusters, charged silver atom in the nanorods. And another one, when you go to the larger sizes, like higher, around 20 atom sizes, this is below this line. So that means this charge ratio is small, charge and charged silver, and the silver size cluster size ratio is smaller than 0.67, and this line is around 0.5. So that means in these cases, they have a higher number of neutral atoms compared to this kind of system. So in this case, you need to get something like this one. So if you think this one, but it's very, now you need to justify the shape, because why the charged silver are the far over there, and then you will get the less charged silver here. So their hypothesis is that in that case, that DNA, these two DNA are not bonded with like Watson-Crick phase. They have another type of bond. I just show you. I just took another picture.
Oh, before you go, can you?
No, I'm just showing you.
No,
Yeah.
just like this magenta color.
Mm-hmm.
So this structure, is it really just kind of a structure, silver metal structure from bulk material? Would it correlate? Like if you just
No.
look on the latest structure,
Completely
no?
different.
So it doesn't look like this if you
Or
just
it's-
take a metal.
It's
Or-
another artistic drawing.
In this case, this is a very simplified one. That's why it's showing artistic. And this is the real. They are optimized. I mean, this is the indicating this kind of.
But it's completely plain structure, or you have some atoms kind of like, you know, like you just look on the projection, or you have your charge guys going up and down like in a different planes, or it's completely flat.
They are flat, but DNA, but they change their flat, what's that called, plane according to the DNA conformations. Because DNA is not a straightforward. DNA is like twisted in a way. But in this, if you compare the tetramer,
But this is single-strand DNA. It should not be twisted.
no. But in this case, they use saying that this formed by double-strand DNA. Single-strand, they are using
You said red ones is a single-strand, green one
yeah,
is a
single-strand DNA, but that single-strand DNA forming the Watson-Crick type, I mean double-strand through the silver. Because now silver is in between these two strands.
Okay.
So it's formed because the silver plus in the either side of this one, and that silver plus is bonded with the nucleotide.
But it can be bonded with any nucleotide. There is
It-
no any.
Yeah,
Because,
that's it.
again, in your double strand, you really have to have your CGAT to create a hydrogen bond. You cannot have CC or CA, right? In a double strand DNA to make this helix. Here, you have. It can be coordinated through silver, but it can be CC, GG, AC. There is no any selectivity with respect to these base pairs, right?
Yeah.
As you have in your double strand.
So it's not it's not a DNA type double strand. It's just a nanorods, and the two strand is attached in the two sides. In that case, I would say.
Okay.
And they also saying that it's suppose like in a small cluster, even you can get it by using the single strand DNA, because single strand can twist it and flip surrounding the small cluster. So because it's not a real straight, like it can bend it and coordinate with the silver by circulating around the cluster. It's good possible in that case too.
Okay. Yeah. Oh my God.
So in other cases, in this case, they are saying that they have two types of DNA bond, like this one is a common one, Watson-Crick, and they have another type of bond, which is known as a Hochstein bond. In the Hochstein bond, their coordination, this bond, form this one. So this atom, this group actually in the other side is a hydrogen bond through this nitrogen bond. So if you got this type of coordinate bond and you form a DNA, the coordinate side and distance between the coordinate side is longer than this one. The distance between this bond is like around 2.6, around 2.5 angstrom. But in this case, you will get the distance between the one unit to other unit around 3.5 angstrom. So because of that, they can facilitate like this one, because this silver atom and this silver atom distance is higher than in this case. So, and they also put some reference. I did not able to download that paper because of didn't have access that one. And they say that in that also can help you to stabilize the silver DNA system. make thermally stable on this type of things. And to considering all of these facts, and they're saying that this could possible to form a 1D nanorod type conformations.
Javad?
Mm-hmm.
I have a really stupid question. Okay, so in the second slide that you just showed, you show the traditional way where we think of DNA bonding through hydrogen bonding interactions between two strands of DNA. So how does the DNA bond to the silver?
So in that they said that so they have two bonding sites. Suppose like in regular one, Watson Crick type one, it can bond it to the nitrogen of the cytosine and adenine, like same as is break the hydrogen bond, and the same atoms are coordinated with the silver. Does it make sense?
So it's just a coordination bond through.
Yeah, it's coordination bond
through ionic interactions.
Mm-hmm. And so then they take the absorption spectra. So this is the absorption spectra of the silver 14 cluster. In the silver 14 cluster, they got a very intense peak here and the second peak here. And the black line, this is the absorption spectra of the nucleotide, what they used. So if you look on here, this peak is coming from the nucleotide, and this peak is mainly from the silver cluster. And now we need to characterize this absorption peak. What is the related to what type of shape responsible for this type of sharp peak, absorption peak here. So there are a lot of reference. I'm just showing you the another. This is not from this paper. They are one of the reference paper. They calculate that theoretically, and by using the metal cluster. And metal cluster always give you this very high intense peak. And this is the. And they also make argument.
But this calculation is based on this without really including DNA.
This is the difference. This one is just a metal cluster, just calculation. And I also showing one of my results. Unfortunately, my atoms is like blocked on the other side. I can move this one. So one of my calculations when I make this is the ligand are guanine and cytosine ligands. I just put them in the around 5 angstrom distance between one, and after optimization I got these like rod-like shapes, and it also giving us the very.
But this is charged.
This one is 2+ charge, yeah. And this is also charge system. This one is I guess 4+ maybe. So this also gives us the same very high intense low energy peak in these cases. There's a very similarity to the experimental one what they got. And now they're showing the argument that type of this one is absorption peak is a plasmon system, plasmon argument system. So they have all other comparison with the experimental result. They give you like 4 or 5 different experimental. And
oh, you need to explain what is plasmonic.
Yeah, so plasmonic is, this would be, I guess, easier to this one. So in kind of plasmonic system, especially in nanorod type things, we will get the 2 different absorption peak, like one for the transversal, and another one is for longitudinal.
But how is plasmonic peak different from regular electronic transition? Why people differentiate?
I mean, why the difference between them, or how we
different? Or maybe they're the same. I don't know. Are they supposed to be different?
They're always supposed to be different, yeah.
So usually you're thinking about probably clusters, not clusters, actually nanostructures of hundreds of atoms, or maybe even more than hundreds of atoms, thousands of atoms, right? So they talk about really like, I don't know, 10, 50, 100 nanometer size structures of silver or of gold, right? And then they talk about plasmons, and they see it in a range of, in case of silver, I think they see it in a green range. So kind of the emission or absorption. So how is it different? Because in your system looks like molecules, but in the case if you're thinking about thousands of silver atoms, it's probably more metallic.
More metallic cluster.
And then your electronic transitions really have very small splittings. They will not really provide you any absorption, should not provide you any absorption in a 2.5 or whatever electron volts, which corresponds to this green light. So then what exactly is the origin of this plasmon peak? What's the mechanism?
It's mechanism through the as an electromagnetic wave to.
So you're still thinking that you need light, right? It's the source of your electromagnetic field. So and you have almost 3 electrons. In the metallic system, even if it's a nano system, the electrons are pretty free to move, right? And then what they do?
So and then.
What exactly, what you say, like they're creating this wave, but what making this wave?
So that wave can change the.
So you put charge.
Electron.
You actually put many charges in the electromagnetic field. What do you expect happens with these charges? Just think about a model, not a real system.
You mean the negative charge or cation?
Some charges. Doesn't matter. Negative or positive in the electromagnetic field. What do they do?
They will show you some dipole, oscillation strength,
They start to oscillate, right?
Oscillation strengths?
No.
Oscillation,
They, like all these charges start to oscillate at some frequency, right? They kind of oscillate collectively together. Kind of making really this wave-like behavior due to the presence of this electromagnetic field. Of course, in accordance, in a response to the whatever the wavelengths or whatever the energy of this electromagnetic field, the light which you shine, right? And these now oscillations of charges also create electromagnetic field, which can be kind of seen as emission. Oh, kind of, now you will have this interaction in a visible range as a response due to this collective motion of electrons or of charges. Doesn't matter which charge you have, glass will be do pretty much the same thing in this electromagnetic field, in oscillating electromagnetic field, because we know light is providing, of course, it's electromagnetic field which oscillates, right? So it's completely different mechanism comparing to the regular UV-V spectrum which we usually see in the molecules or
cluster,
quantum dots and so on, right?
Can DFT or TDFT catch this effect?
No. We need to do like LR speed.
But then how do they calculate this plasmon effect?
Yeah, so they didn't calculate this one. I'm just giving you showing the example of the another paper from this paper. So they calculate the plasmon by that the method LRs. I forget the exact name of this one here. 4-letter name, the method here.
Huh? What?
They have a method.
Finite differences Maxwell equation?
No, they didn't use that one here.
They were not using Maxwell equation?
I did not go through this whole paper, so I just said the result one here. So thing is, their argument is like, if it's, this one is a plasmon, so you will get the 2 peak, 1 peak, this peak is a result from the longitudinal movement and it's known as a L peak. This one is a T peak or transverse. And this energy is actually in these ranges, so they
when you say again longitudinal and transversional, right? So again, it depends on the way how you can collectively move or oscillate these electrons, because they can oscillate in different planes, right? Either along this or along that. And this kind of differentiate.
So they're saying that this atom, they're considering the single atomic layer, so they're saying that this band should be in the constant, but this one is in this range, so they didn't able to resolve this one. But this peak is belongs to this compared to the so-called L peak here in the from the plasmons.
But again, in this paper, they can see the infinitely long chain of these atoms.
In this paper,
yeah,
this is the atom like 1 to 18.
Oh, so it's still finite structure.
It's finite structure.
Finite number of electrons.
So if this is true, so this peak supposed to redshifted if you increase the length of the quantum nanodots. So in this peak, they are giving a same example, like they got this different peak and is moving these directions, but to the low energy direction by changing the nanorod length. And these all are giving you the one peak, and this is moving. So from this argument, they're saying that this is a single atomic layer, atomic nanorods, atomic thickness, and also this peak is responsible to the length of the nanorods, and then it's going to change the shape according to the nanorods. So in the next one, then there's the same question already asked, that why they are taking these nanorods, not spherical shape or all other shapes. So there are some in these cases. First, they're trying to showing here this peak. This peak is the first energy peak of the different shape nuclear silver cluster,
And again, this is calculations or
no? This solid line is experimental result. This is the first energy of the first peak of different cluster, and this is the calculations of their by considering as a single layer nanorods. And they also calculate the another energy by considering that this nanorod is one silver atom is surrounded by the 5 silver atoms, and then it's propagated to 2 directions. So in that model, it's above all of this experimental result. So they're saying that, and this is all of the spherical shape cluster energy at a very high energy. So they're saying that it's also a seemingly good agreement with the experimental result. So this is another proof of this nanorod structure. And for why not the cluster? So I mean, a spherical cluster, they are saying that in a spherical cluster, when you add the positive silver atom, because a spherical, you can use the Jellium model, like free electron models of the spherical cluster to explain the absorption spectra. If you add the positive ion, positive silver, it's not increasing the free electron, but it increases the volume of the cluster. So that means it should increase the first energy peak. I mean, to the blue shift energy peaks. But experimentally, in this study, we got that increasing the shape, adding the cluster shape, the first peak is moving to the red directions. So in that case, it's not comparable with the spherical cluster. And another thing is, I don't understand this theorem and everything. I just put this here. According to this one, they're saying that if we use the very high positive charge cluster, it can spill out the effect. It become like that. If you increase the sizes, you will get the same energy peak in absorption spectra. First absorption spectra shouldn't be go to the red or blue or red shifted due to the increasing the size. If you consider this type of thing like a spherical cluster and high charge. So both of the observation doesn't match with their experimental result. So it gives us the background of the comparison of their methods with the experimental result. I mean, nanorod things. And this is the here. So as I said, a spherical cluster, I'm just showing you some example from the spherical cluster. If you look on the spherical cluster, it's not showing the very distinct low energy peak. It's giving an absorption spectra almost in the same energy ranges with increasing.
But this is not with DNA, right?
This one is the DNA. Sorry, sir, this is not the DNA. This is with the
sial groups shown as surface. But you forgot probably to mention in the very beginning the problem if they use anionic ligands, such as like sialate, right? So then this same as silver or gold, both of them not really very emissive. But when they do it in DNA, encapsulated or whatever, wrapped or whatever they call it, then they becoming really strongly emissive, very emissive. And interestingly, gold is not emissive even when it's grown in DNA, but silver is emissive. And again, people don't know what exactly the mechanism, but the bottom line is that ionic ligands, although we know the structure and can really use it for kind of a clear understanding the structure, they don't have emissive properties. But with DNA, no one knows the structure.
Yeah, but they're able
what
to
exactly DNA is doing and how is it wrapped, but they're emissive.
Yeah, they're able to get more than 90% quantum error in the sum cluster in this experiment.
Okay, emissive only for silver. No one were able to get the gold to be as. I mean, they also have better emission properties than sialate guys, but probably even not like really orders of magnitude low comparing to silver.
So this is a few examples of the absorption spectra in the spherical cluster. I'm just showing you as a reference with the because they're comparing with the other one. So there are some emission absorption spectra, emission result. This is just an image of the emission, and then they also shows they mention there is a non-obtain blinking things of this system, and this emission spectra is emission taken at a 1.7 Kelvin temperature. But they're saying that at even at 1.7 Kelvin temperature, the line width of this spectra is comparatively higher. That means its decoherence faster. Is decoherence faster.
Which temperature again you talked about?
1.7 Kelvin.
Oh wow.
Yeah. So this 1.7 still is not a very sharp. Is like the other line, and this is because of this thing. Is because of their 1D system, a 1D system, and then
because of what?
1D, I mean nanorods type things here. So it's increasing the decoherence time. Sorry, decreasing the decoherence time. So they didn't go like distance in very long discussion on decoherence. Just mention one line in this case. And this one is a polarization, circular polarization experiments. I don't have that much experience on this one, but what they say, that's why I put the whole things here. Actually, I don't remember everything. So they can, at this experiment, the polarization dependence can be explained by this formula here, and this B is just constant. So M is dependence on the cluster shape and cluster sizes. Cluster means your media, your subject directions, everything. So if it's spherical, this M is supposed to be the close to 0, and if it's the 1D materials like nanorods types, and it's supposed to close to 1. So if it's close to the 1, at the different angle, it should give us homogeneous shifting everything. So this M also indicating that what is the I forgot the exact term. What's the similarities between phase difference of these two waves. So if you look at these is the two different cluster, but they have a similar shape. Shape means like phase is similar. Phase difference is same in constant with the different polarization angle. So it's because they calculate, put everything here, and they calculate M is close to the 0.9 here. So this 0.9 is close to the 1, which is for 1D, nanorod type things. So that's why they also conclude that their hypothesis is true from this experiment. And this one, so that's all about the first paper, their experiment, and this one is their second paper, what does it say? I put
your
both
call will be disconnected.
Because it's...
Levi?
Yeah, they're done.
They're gone, okay.
Because it was just for by 6:15 or something.
So I put everything, I mean, very brief result from this paper. So they also did almost similar things. As I showed in the first slide, they do the mass spectrum. They predict the charge and cluster size, and then took the absorption spectra. And then they hypothesized other things like it's not forming like cluster, I mean, not as a cluster, it's forming as a, they say, supramolecular, as a molecular system. And the molecule conformation depends on the how it's interacting with the DNA base. And if you change the DNA base conformations, it can change these supramolecular or molecular clusters, nanocluster conformations things. And they said they synthesized different type of things. I'm just going three different cluster. Which one is blue emissive, green emissive, and red emissive. I'm just showing the two, green and red one. In the green one, they're saying that this one first is nucleation. Nucleation started with the silver plus. It's bonded with one side of this one, and then more silver atoms coming, and then they form make equilibrium. This is the bigger image of this one. So in this case, if you look at here, this silver is coordinated with the nitrogen from the two cytosines, and this silver is coordinated with the other nitrogen of the next cytosine groups, and then another nitrogen is coming with this one and form triangular shapes. And when they calculate their theoretical absorption spectra, is giving you the nice agreement with this experimental result. And another one, what's happening in the red emissive diagram? In the red one, they're showing that instead of the forming a triangular shape, is forming nano rod type things, like each silver is bonded with the separate nuclear base and form this kind of thing. And the interactions is differences here, because if you look at here, these cytosine are one after another, one part in this. And this is the reason of the forming their red
How
clusters.
many atoms again?
In this case,
the same number in both cases or not?
So in this, they're saying the main cluster is a 4. In this one, the main cluster is forming a 3.
But in previous slides, you were showing that if the size is lower than 10, then it's not emissive.
Yeah, in that case, yeah, they're also saying that it can change by changing the nuclear base types. But in this paper, they are showing the emissive, but I guess because this is the experimental one, but this is not exactly whole cluster, because there are some other atoms here too. So they have interaction with these things. I mean, this whole thing, whole supramolecules too. So from my perspective, I would prefer to say this is not only because of this 4. We need to compare this, we need to consider this other silver too in whole thing as a one supramolecule system, not as a one piece. So their conclusion is, if you change the order of this base pair in a nucleotide ligand, they can change the formation of this cluster, formation of shape of the cluster, and it will change their absorption spectra too. And when they took this one, and they're also showing the NTOs, they're saying that they have a charge transfer. They mentioned the charge transfer to the ligand, but it's actually showing the charge transfer, D to D charge transfer, with the contribution of charge transfer to the ligands. And they're saying, because reason of the red cluster is the charge transfer to the ligands. If you remember, I showed you one of my calculations. This is this one is the NTUs of that system. Is showing that more like metal to metal charge transfer, and this becomes a bright in my calculation speed. And although they're saying that the metal charge transfer to the ligand is also significantly showing the charge transfer to the ligand and D2DD. It's also giving us a similar good similarities with my experiment too. So from these two papers, I'm just to conclude this whole paper in one slide. From these two papers, one thing is clear: it's not in the DNA system. Silver is not forming a cluster. If we form a cluster like 2D cluster, 3D cluster, maybe it shouldn't give us experimental agreement with experimental result. It's almost confirmed to form nanorods or rod type things. Or another thing is, or it may form the subcluster like this small cluster and the other one interacting this one.
Oh, by the way, and this is also charged? What?
Yeah, this is all. This one is as I guess 2+. Correct, but charge obviously, yeah. And it's also confirmed almost all calculations. Silver always form a charge cluster. This is the question: so what is the oxidation state? +4, or what is the ratio of the charge and sizes? But always form a charge cluster is for true.
But so, their spectra, just kind of to get some technical details. So do they calculate like the structures which you're showing, right? It's exactly the systems which they consider, like they not just consider reduced model. It's exactly with all these nucleotides.
Yeah. So this is the optimized structure after calculating the QMM method. They consider these all ligands by classically and this system only quantum mechanically.
And then they get in this spectra based on the QMM.
Yeah, and then getting this spectra. And this one is the optimized one after the methods. This one and that one too.
Nice. Okay.
So this is all about these two papers. And conclusion is very just 1 or 2 lines. That's why I didn't put on the slides here.
Hey.
Okay. Well, thank you.
So.
Any question?
Yeah, just we have to be by 6:30. We have about 5 minutes. Any questions? No?
Everyone is so excited.
Okay, so then let's close it.
Let's thank Jebet once again.
Yeah. And, so we hope to shift our time for Fridays from 4 o'clock to 2 o'clock. Depends, of course, on the.
So would it be